liquid and depth of a liquid. You don't have to worry too much about this derivation other than to sort of follow along with the thought process. So the first thing you should realize is that the deeper I go in the liquid, the higher the pressure will be. And I think you've probably all experienced that in a swimming pool, right? Kind of you float on top, and you've got atmospheric pressure on your back. And if you dive down into the pool, not only do you have atmospheric pressure on the surface of the water, but you also have the water above you pushing down on you. So that implies at the new depth, h, let's say this is the surface of the water, if you go down to this new depth, it seems quite reasonable that the pressure should be higher. I think that's reasonable. Okay. So if we were to take this representative block of liquid, whatever it is, fresh water, salt water, mercury, it doesn't really matter. If I take this representative block of liquid and I assign P1 to be the pressure at the top, and I assign an area A1, or A, at the top, I can come up with the force. Don't forget, pressure is force divided by area. So if I multiply pressure times area, I get force. So there's a force down on the top of the liquid, P1A. Likewise, there's liquid pushing up on the bottom of this representative block. That force is P2A, yes? Okay, so I've got up minus down, and there's also just the weight of the water in the block itself, or the liquid in the block itself. So there's three forces acting on this thing. The weight of it, the force from the top, and the force from the bottom. Up minus down, if it's not moving, because we're talking about static fluids, not moving fluids, right? I can write the sum of the forces in the y direction equals 0. You guys following that idea? It's beautiful. All right, so P2A equal P1. Is everybody comfortable at least where this came from, more or less? Okay. So the next thing I want to do is go ahead and divide by area. Oh, actually, yes, I do. Okay. But before I do that, I'm going to make an adjustment here. Oops. All right, so the mass, remember rho is mass per unit volume, right? You guys remember that?
Yeah.
So I can represent this guy here by rho times V times G. This is mass times G, mg. All right, now if I divide by area on both sides, area of top and bottom here, I get P2 equals P1 plus rho V G over A. Now, what is the volume of a box? Length times width times height. And I told you that this is area A, so this is length times width. That's the area. And the height here we'll call H. So if I divide volume of a box by the area on top and bottom, what am I left with? The height. So this is the relationship between the pressures in a liquid. Oops, that's a plus. The pressure lower down in the liquid is equal to the pressure higher up plus the additional pressure due to the column of liquid above you. Stop, you're blowing our minds. No more. Guys, calm down now, calm down. This is the important outcome. So let's think about it. Here I am in a swimming pool. If I'm at the surface, what's the pressure at the surface? Not zero.
Pressure, atmosphere.
Atmospheric pressure, remember, it's pushing down on us everywhere. So the pressure here, P1, is atmospheric pressure. So if you go down a distance h, you can now calculate the pressure lower down in the water. Well, it's going to be the atmospheric pressure from the top plus the pressure due to this column of liquid above. Do you see? There's two things at play here. Atmospheric plus however much liquid is above me. Plus rho g h. And we'll talk about this h thing here in a second. Is everybody at least comfortable with that boxed equation and this simple thought process of being at the surface of a pool versus deeper in a pool? Yes? Oh, yeah. Okay. So here's the part that's going to really blow your mind. Okay. I really want you to listen to what I'm about to say and take it to heart. The pressure lower down in the liquid is the pressure higher up plus the density times 9.8 meters per second squared times the height of the liquid above you. It does not matter the shape of the water. Whether if I have this going on or this going on, or this going on. If this is H, and this is H, if these vertical distances are all H, the pressure here, if this is open to the air, for example, and the pressure here at a distance h farther down are all the same. It does not matter what shape this water is in, as long as we are some distance h below the surface, this will be the relationship between the pressure higher up and the pressure lower down in the liquid. It's just the vertical distance h that makes the difference. Okay. So look at this thought experiment. This is in your book. It's a really cool thought experiment, actually. How many have been to Hoover Dam? It's pretty cool. If you haven't been there, you should do it. But don't do it between Christmas and New Year's. It's very crowded. Did it a couple years ago. It was crazy. That was the second time I've been there. Anyway, so this is, I believe it's Lake Mead back here, right? Look at that thing. It's way out here, right? So here's the thought experiment. If I were to drain, oh, by the way, before we get there, you realize that Hoover Dam's really thick at the bottom. Why?
There's a higher pressure on the water.
Because there's higher pressure. So it's that pressure at the bottom of the dam that is pushing against the bottom of the dam. Okay, and because it's way down below the surface of the water, right? Now here is the thought experiment. If I were to drain Lake Mead, get rid of all this water back here and only have this simple column of water right next to it. Does the dam need to be the same thickness? We've got two yeses. I had a head nod, a yes, and a no. So the head nod, I don't know what to make of that. Double head nod, triple head nod. Does it matter?
Like you just said, only the height matters, not the.
Only the vertical height matters. I could drain Lake Mead and make it look like this with a little tiny bit of tiny lake, mini Lake Mead right next to the dam. I still need the same thickness of the dam because the pressure on the bottom of the dam is only a function of how deep the water is, not the shape of the water at the top. It's irrelevant. Yes,
This is assuming it's static and not like flowing into the.
that's different.
Okay.
For statics, yes. Okay? We have all kinds of crazy things when fluids move, the pressures change.